Okay, so in problem number 2, we saw that when r was greater than or equal to 1/2, that an instability occurred and that the graph started to oscillate. And so now in number 3, we're going to be performing a von Neumann stability analysis to see why this occurs. So first thing I'm going to write up here is the heat diffusivity equation that we got once we plugged in the thermal diffusivity constant. So this was we're dealing with this in number 2 as well. And so now I'm also going to write down the variable Tk is equal to e to the I k x e. And here I is equal to imaginary number, k stands for heat conductivity constant, x is position, and t is time. And so we're going to be dealing with Tk here quite a bit, but also I'm going to really quickly write down the Euler equations, and that's because we are also going to be dealing with these as well. So I'm just going to write them down here real quick. And we have positive and negative here because of 2 different functions of sine and cosine. And so I'm just going to box that in over here. So we're reminded of them, but we're going to come back to them here in a little bit. And so now we're going to take a look back at Tk. And so we can think of Tk as a summation. So let me do this in a different color here. So Tk equal to summation of k equals infinity, k equals negative infinity to k equals infinity, and ck of e k alpha k squared x. Okay, so like I said, we can think of Tk as a summation of our actual temperature profile. And so then what we're going to do next is we are going to write down the finite differencing equation that we derived in problem number 2. So that was Tj plus 1 to the n is equal to Tj n plus r, which is all equal to Tj plus 1 to the n minus 2. Tj n minus Tj minus 1 to the n. And so now, using our summation, we are going to be able to solve for Tj plus 1 to the n and Tj minus 1 to the n. And we are going to get n and Tj minus 1 to the n is going to be equal to e alpha k squared t n. So now that we use the summation to solve for Tj plus 1 to the n and Tj minus 1 to the n, you see that we are able to plug these terms into our heat diffusivity equation up above. And so I'm going to do that in a different color. Here. Right, so we can plug that in here and here into this equation and get T. And now you see that once we plug that in, that we have a Tj to the n in every term on the right side of the equation. So we are able to pull that out and simplify the equation down to and I just realized I wrote these a little bit wrong here. This is change in x, and this is so I did write those a little bit wrong. Let me change that real quick. And so now that we have this equation right here, we're going to be able to plug in our Euler equations. So let me erase some of this up here. Okay, so we are able to plug in our Euler equations, and that's going to simplify down to and 2 cosine change in x. Oops. And that's because the signs cancel out there. So now we have this, and so I'm just going to erase this down here. And so now we're going to be looking at the R value in the 1/2 situation that we are concerned about. And so we're going to be looking at this term right here specifically, and we know that cosine oscillates between -1 and 1. So we are going to set this 1. And so then we are going to pull the 1 out, and it's going to be -2 less than R. And so then we can also pull out 2 and have -1 R. And so then we can also pull out the negative 1 plus 2. And then when you do that and you solve for r, you get that 1/1/2 is, you have to switch it, the sign. So basically for the amplitudes of sine and cosine, once your r gets to be equal to or greater than 1/2, you're going to have stability issues because of that multiplicative factor of sine and cosine. So therefore, to use this equation, you're going to have to make sure r is less than 1/2 in order to remain stable.